Okay. Now we will see analysis of a frame by using moment distribution method. Analyze the frame shown in figure using MDM. A simple problem will take, because that's how in the exam also they ask you. This is A, B, C. This is 3 meters I, 4 meters I. This load, let us say 12 kilonewtons per meter. Okay. Now, this is our problem. Now, earlier when I solved the earlier problem, first step was to find the fixed end moments. Fixed end moments means assuming that all joints are locked, then what are the moments required to lock all the joints? That means don't permit the slopes to happen. For that, how much movement is required? That we have listed for the span AB, for the span BC. Since we know fixed beams subjected to UDL or point load, what are all the fixed end moments, that step we should not write even in the rough work also in the exam, because you have only 2 minutes time, and that 2 minutes time effectively you get 1 minute time for the calculation. In 1 minute time in the rough work, we should not write all the stories. So one by one we'll skip off the steps. First problem I solved all the steps. Second problem we'll skip the first step. That means finding the fixed end moments. Next problem, second step also we will skip it. Third problem onwards, third step also we will skip it. So we will see how to increase or how to do the problems fast. Finally, not only your ability to solve the problem, but how quickly you solve the problem is also equally important. Okay. So for the span AB, no loads, MFAB, MFBA 0, no fixed end moments. MFBC anticlockwise minus WL square by 12. That means minus 12 into 3 square by 12 minus 9. MFCB clockwise plus WL square by 12. That means plus 9 kilonewton meter. That again we don't have to write. We can read by inspection itself. Now second step onwards we will start. What is that second step? Distribution factors. Distribution factors, I told you, at a joint if only one member is mating, its distribution factor is 1. Because there are no other members are there. Once fix it and release it, only one member will share, will take the moment. Other member, if it is a pin, it cannot take. Now if you see at A, how many members are there? At A, not only one member, that fixed support means someone should be there to fix it. At A, there is a footing, and that footing rests on the soil. When compared with the flexural stiffness of the column, flexural stiffness of the footing is very high, maybe 7 to 8 times more. We idealize that situation as if it has infinite stiffness, because column dimensions, let us say 200 by 200 mm. Then footing dimensions will be 1.5 meter by 1.5 meter. Thickness is 15 centimeter concrete. We idealize such a big thing as a infinite stiffness member. So one here at 8 there are two members, footing and column AB. At B also two members. This we call it as fixed support, means that the slope is 0. Two members are mating but slope is 0. At B we call it as a rigid joint. BC and BA, two members are there. But when you apply moment, these are relatively comparable stiffnesses only. So when you apply a moment, both will share, because now the distribution factors will come. So we call it as a rigid joint. The difference between rigid joint, fixed support is only that. At the fixed support condition, one member has infinite stiffness. so that it will not permit the members to rotate. Rigid joint, it will take the moments, it will rotate the members also. Other than that rotation, there is no difference between rigid joint, fixed support. Okay. Now let us see at A how to find the distribution factors. We list them out. Joint, member, K, sigma K. Distribution factors are K by sigma K. Okay. At A, two members are there. One is footing, second is AB. Footing stiffness, relative stiffness, we will take it as infinity. That means compared with the column, very high stiffness, so we idealize this as infinity. AB member, when you stand at A, look at B, because you are locking all the joints, B now behaves like a fixed support. It takes the moment. After that, it may rotate, but it will take the moment. So we idealize this as a fixed support. I told you no difference between fixed support and rigid joint. That rigid joint behaves like a fixed support only, but only difference is it rotates. Okay. Now AB member, it is 3 by 4, no, I by L, I by 4. Sigma K, very large value plus very small value. You take it as very large value. Okay. So infinity by infinity. We should not think that infinity by infinity, how it is 1, it is indeterminate. Mathematics teachers told us that it is indeterminate. But here infinity means very large quantity is the idea we have to keep it in mind. Very large quantity by very large quantity is like 1. Very small quantity by very large quantity is like 0. Like that. So distribution factors are 1, 0. That means at the fixed support, like at the footing level, if at all you apply 100 kilonewton meter on the footing, entire moment is taken by footing only, column will not take any moment because its distribution factor is 0. 100 kilonewton meter when you apply, 100 kilonewton footing will take, 100 into 0 is 0, column moment is 0. Even if you take wall, fixed support is there, a propped cantilever beam is there. At the propped cantilever fixed support, you apply 1000 kilonewton meters, say, beam will not take any moment. That's what we have learned in strength of materials. So entire moment wall will take, nothing will be transferred to the beam because its this member distribution factor is 0, wall distribution factor is 1. Okay, so this is the case here. Next, come to the joint B. You have BA, then BC. Standard B, look at A. It is now like a fixed support because it takes moment. So you have to take it as I by 4. Standard B, look at C. C cannot take any moment. So when it cannot take any moment, reaction is 0. Then we have studied that its stiffness factor is 3 by 4, I by 3. So you will get I by 4. So I by 4 plus I by 4, 2I by 4. This is 1 by 2, 0.5, 0.5. Now what we have to do is you have to see the how the calculations will come. Standard B, when far end is fixed 4 meters, far end is hinged 3 meters, then distribution factors are 0.5, 0.5. Most of the times this type of question only will come so that your calculation time reduces. Okay. So this is your second step. Next, third step is your end moment distribution. We'll write here. Third step, end moment distribution. Next problem, we will skip the second step also. End moment distribution. Joint, We have this is joint A, joint B, joint C. Here distribution factors at A, this is 0. Then where is 1? Left of A, there is a footing. Footing, since we don't deal, we take it as, if you want to write here 1, 0 also you can write 1 is footing, A is at the joint A, one member is footing, one member is AB. At B, two members, BA member 0.5, BC member 0.5. At C, distribution factor is 1. Then where is the other member? Other member is the pin. Pin distribution factor is 0. So 1, 0. So CB member distribution factor is 1. That means at C, on the member CB, whatever moment you apply, CB only will take. Pin says I cannot take. Like that. At the support, fixed support, whatever moment you apply, support will take. Member says I cannot take, because the relative stiffness differences are so much. So here it is 1. Now let us see. This is the fixed end moments. MF AB 0 here, 0 here. MF BC minus WL square by 12 minus 9 plus 9. If you forget how it comes, this is the formula. WL square by 12. W is 12. L is 3 square by 12. This 9 comes like this. We should not write in the rough work MFB says minus W square by 12, so minus 9. That will waste our time. Minus 9 plus 9. These are all the fixed end moments or the locking moments required to make the slopes 0. Now, let us see how the end conditions are. At A already fixed support, so don't unlock it. It is a locked one. B is also not locked one. It rotates, so we will release that. C is also not a fixed support, it is a hinge support. Moment at C has to be 0. So those 0 moments we release completely at once. Okay, so that is called release. So first we will release C. Releasing C means, I told you last class, releasing the fixity, or in other words, releasing the lock. To lock the joint C, you require plus 9. To unlock it, that means to fix it 9. To unlock it, minus 9. That is called release. I told you 2 marks question also. A propped cantilever subjected to eccentric point load. Then what is the fixed end moment at A? First you fix them. Why you have to fix them? Only then you know, for that only you know the formula. So first fix it. Since it is not fixed, release. Then half moment is carried over. Now you know how to find the final moment. So an unknown problem you are converting into a known problem and solving the problem quickly. Now this is the fixed one, plus 9, but actually it is not fixed joint C. So now release. So minus 9 you have to apply. Release C means minus 9. Who will release? We only have to go and release. So when you apply minus, see, all the joints are locked now. Only one joint you unlocked it by applying minus 9. Because this B is a locked one, means fixed one, half the moment is carried over. So carry over moment. From here, how much is carried over? Minus 4.5. Now you can get net fixed end moments. Okay. Net fixed end moments. Not final, net fixed end moments. This is now 0. Here also 0. Minus 13.5. This is 0. Now this net fixed end moments, what they tell us is, to fix or to lock the joint A, we require 0 because no load was there. To lock the joint B completely, you require minus 13.5. There is a minus 13.5 kilonewton meter existing at the rigid joint B, so that theta B became 0. So fixed like that. C you have completely released. Now you found that B is also not a fixed support, a fixed joint. it rotates. That means unnecessarily you locked the joint B. All intermediate supports you unlock at once. In the exam, you will have to unlock only one because 2 minutes time only is there. Otherwise, it goes to there. Half the movement is carried over because you locked it. Then you have to unlock it, again release it. Half the movement will come. But that like that 2-3 times means we cannot do in 2 minutes time. So the questions are like this only. Only one balancing only task we have to complete. Then after that, nothing will be there for us to do. In 2 minutes, our task must be that only. So to fix this one, you require minus 13.5, but we don't want to fix it now, release. Means plus 13.5 you apply. That is called balance. Release or balance. Release or balance B. When you apply plus 13.5, 13.5 gets distributed. At B, you are applying 13.5 plus. So two members will share. So 13.5 plus 13.5 into 0.5. 6.75, that much you will get. So you will get here plus 6.75, 6.75 like this. So when you apply this 6.75 is this one. You applied 13.5, this fellow took 6.75, this fellow took 6.75. When there is a 6.75 clockwise, how much is carried over to A? Because it's a fixed one. A is a fixed support. So carry over moment. Out of 6.675, half will be carried over here, 3.375. From here to here, nothing will be carried over because C is a hinge support. Now the final end moments. What you get now is final end moments. Fixed end moments are different. Final end moments are different. Fixed end moments are the moments required to make the slopes zero. Final end moments are at the rigid joints also. Final end moments are after rotation. What are the moments existing? So when at a rigid joint, you see slopes will not be zero. They rotate. They take moment. They deform. They rotate and stop. So final end, then what you get is the final end moment, which can be different from fixed end moment. So final end moments are this much, 3.375. This is plus 6.75. This is minus 6.75. This is 0. That means if at all you want to fix this one, minus 9 kilonewton meter is required at joint B, two members if you want to fix it. Once you release them, 9 became 6.75, 6.75. Both will share. Both members will share. Some of these end moments at the joint B, some must be 0. Otherwise, joint will not be in equilibrium. So if this member takes 6.75, that member also should take 6.75. Otherwise, that point will not be in equilibrium. So these are now final end moments. So this is your third step. In the exam, they give you the problem. Your task in 2 minutes time will be, they ask you what, they give you the frame, loading they give. Question will be, what is the moment at A? 3.375, that's all. So this process you have to complete in 2 minutes time. Another way is, they give you the moments, they will ask you to find the reaction at A. That means horizontal reaction or vertical reaction, like that. For such cases, if you have to find the reactions, they solve this problem for us. These moments they will give us. MAB how much, MBA how much, moments they give in the problem itself. Then you have to draw free body diagram of each member to find what is the horizontal reaction, what is the vertical reaction, etc. Okay. Now let us see that part. Now this diagram I'll remove. Now your fourth step is support reactions. Earlier problem I told you, we have drawn boxes because all are beams only. So you can draw VA for one box, VB for one box. That type of boxes we cannot write for a frame because one reaction horizontal, one reaction vertical boxes you cannot make it. So on the free body diagrams themselves, we will show all the forces. So this is the member, AB member, BC member. Sufficient gap we will give it. This is A, B, B, C. There is a load here. This load is 12 kilonewtons per meter. Length is 3 meters. There is no load here, but span is 4 meters. This is applied loads. But on the members, end moments also are there because of the continuity at B, because of the fixity at A. There will develop the some footing will exert some moment at A on the member AB. That also we have to show. Those final moments are this one. How to read this one? At A, for the member AB, plus 3.375 clockwise. This value is 3.375 kilonewton meter. A for the member AB. Now come to this one, 6.75 at B for the member BA, plus 6.75, plus means clockwise, 6.75 kilonewton meter. Next, at B for the member BC, minus 6.75. You should, because it is minus only, you have shown anti-clockwise. So again minus we should not write. 6.75 kilonewton meter. Here at C for the member CB 0. So 0. This can be clockwise or anti-clockwise because it's only 0 force. Okay. This is called free body diagram. Free body diagram means it is the diagram of a body on which what others are doing we have to show. Okay. So this is the beam, free body of the beam. On this applied loads we have shown. Who will give this minus 6.75? Column AB will give to the member BC. If it cannot give to this member, it will fall down. So what column is doing you have shown, what applied load is there we have shown. Next we have to keep it in equilibrium. It should be at rest. So what are all the other forces they are exerting on the member BC we have to see. Now you see 12 into 3, 36 kilonewton meter down. To balance that, because it is uniformly distributed, the reactions will develop here and here. It's like a simply supported beam. You have to visualize 12 into 3, 36, 36 by 2, 18. Simply supported beam reaction is WL by 2, WL by 2. So 18, 18 over. Next, because of the end moment. Because of the end moment, what are the reactions you see? 6.75 anti-clockwise. To balance it clockwise, reactions will develop M by L. A couple will form like this. Anti-clockwise means clockwise. You see how your fingers are moving. Here it is going up, here it is going down. Now how much is the moment? 6.75 M by L. So you will get 2.25. This is also 2.25. These are individual effects due to applied load 18, due to moment 2.25, 18, 2.25. Now, from the principle of superposition, we can add them. So, 18 plus 2, 20. So, this is 20.25. This is final reaction. Here, 18 minus 2, 16 means 15.75. The red colored ones are from the principle of superposition final reactions. Like this we have to show. Now, when it comes to the free body diagram of the joint, 20.25, who will give? AB member only, BC it should give. This 20.25 is excited by the column AB on the beam BC. Why should it excite? Because this fellow is resting on him. So this fellow will press him. In return, column will press him up, push him up, so that it will be in equilibrium. So 20.25 is the force exerted by the AB on BC. Now when you are drawing the free body diagram of AB, what that fellow is doing here you have to show. If this is 20.25 up, here it should be 20.25 down. Now you see sigma y satisfied here. Then to balance this one, 20.25 here up should be there. The effect of this will be felt on this column like this. Next, coming to this member AB. Whether it is in equilibrium or not, let us see. Clockwise 3.375, clockwise 6.75. Both clockwise only. Applied load is not there. So reactions due to load is 0. Due to moments alone you have to take it. Both of them are clockwise. To balance it, anti-clockwise. See how my fingers are moving anti-clockwise. Right, left. If you should not move like this, because that will not form a couple. Perpendicular distance must be there. So like this. Like this. How much is that? M by L. Total moment is how much? 3.375 plus 6.75 by 4. So you will get 2.53 kilonewton left. Right side here 2.53. Now you see this is now completely in equilibrium. Okay. Now this blue color arrow mark is excited by whom? On the column footing. Footing will press him right side like this. Then who gave this force to him? This member will push him like this to keep this fellow in equilibrium. Now since you have drawn this one, this effect will be felt on this one. So to balance this force, that means in this free body diagram, the effect of this will be felt. This is given by this fellow like this. So what this fellow will do on this is like this. So that the joint will be in equilibrium. This is 2.53 kilonewton right side. When you push it right side, there is a hinge support here. That will exert a force left side, 2.53 kilonewton. Now each free body diagram is completely in equilibrium from sigma x 0, sigma y 0 and sigma m is equal to 0 considerations. Such diagrams are called free body diagrams. If this free body diagram goes wrong, your solutions will never be correct. That means whatever unknowns, when you are drawing the axial thrust diagram, shear force diagram, bend moment diagram, everything will go wrong. From this diagram you can get the values quickly. For this reason only, in first year in your engineering mechanics, there are 3 units you have studied on how to draw free body diagrams. Friction chapter, equilibrium chapters are there. Like that, there you have known when the body is moving right side on the body, how the to prevent relative motion, how the frictional force will act. So which direction, who is exerting on whom? So many issues sirs might have told you. So that is like a training for this type of free body diagram. Who is exerting on whom how much force, like that. So with this support reactions, all other quantities we can find. Now let us see the shear force diagram. Fifth step, shear force diagram, bend moment diagram, deflection profile, and ATD, axial thrust diagram. All the diagrams will draw now. Shear force diagram when you are drawing, it goes something like this, right? This is our member A, B, C. How to draw the shear force diagram? You have two free body diagrams, two independent shear force diagrams for two simply supported beams. If you draw and attach them, it becomes a frame shear force diagram. Always we stand inside the frame so that it will tally with our already learned sign conventions. You stand here, look this side, look this side. Then the diagrams that you draw will tally with our the already learned shear force and bend moment diagram sign conventions, which is sagging, hogging, everything will match. Now you see, again it should not take more than say 20-30 seconds time. This is the frame, stand here, come here, now stand here. Stand here, look left. This is left side, this is right side. Section left side downward. Positive shear or negative shear. This is the shear force sign convention. Right side upward, left side upward, right side downward, positive shear force. This is negative shear force. Right? This is the shear force sign convention. Whenever you are drawing the shear force diagram, this sign convention you have to use. Section left side downward. Now I am turning here. Section. When you are standing here looking this way, for you this is left side, this is right side. So section left side downward is negative. So minus 2.53. Then how it varies? So first stand here, section left side downward is 2.53. Now stand here, section left side 2.53. Like that, at two sections you stand there, look one side. If same magnitude is there, it means that shear force is a rectangle because it's not changing. 2.53 negative. This is minus. Once you show this minus value, whether you write above reference line or below reference line, it doesn't matter at all. Okay, that is for the beginners of above reference line positive, below reference line negative. That is for the fundamentals like simple beams. Now our choice, wherever you want, you can show that. 4 meters, this is also 2.53 kilonewton. So shear force diagram for one simply supported beam is over. Coming to BC member, shear force diagram. You cannot stand here and say section right side upward 20.25 negative, because if you stand here you will fall down. You must stand on the beam. Section left side upward positive, so plus 20.25. So first you show that 20.25. This value is 20.25. Next, when UDL is there, till the end of UDL you have to travel. Then it varies linearly. Now here, don't cross the C, you will again fall down. So just to the left side of C, stand there. Now you have the option to look left side or right side. Anytime you have that option. If I look left side, I must do 20.25 minus 36. Calculate unnecessary waste of time. Instead of that, I will see right side. Because you are sure that whether I see left side or right side, I must get the same value. So now section right side upward, 15.75 is negative. So 15.75 negative. Just join them. This is a straight line. This is positive and this is negative. This value happens to be 15.75. This length is 3 meters. Like that, three independent shear force diagrams you add. Draw them, connect them. That becomes shear force diagram for the frame. Next, bending moment diagram. See here. This is one member. This is the other one. Okay, this point is A, B, C, 4 meters, 3 meters. Then how to draw? Again, stand, go inside the frame, stand here. Section left side clockwise. Will it sag or hog? It will sag if you stand here. If you stand here, it looks like hogging only. If you stand here and see this one, it's like a hogging. But always we should stand inside the frame and decide. Look this way and this way. This is over say. Then when you go to other members, other pan a bay, let us say, then you have to keep on moving right side only. Okay, so this is over. Now section left side clockwise, it will sag. But same clockwise movement here, section right side, it will hog. So minus 6.75. This clockwise movement produces negative bending moment. This clockwise movement produces positive bending moment. So you are drawing the bending moment diagram. Now bending moment sign convention only you have to see. How it deforms you have to see. Bending moment sign conventions I told you are deformation sign conventions. Now based on how it deforms, you have to decide whether it is positive or negative. Accordingly, you have taken if it sags positive, if it hogs negative. So coming to this one, this is hogging 6.75. You can show outside like this 6.75. 3.375 you can show inside. Don't want, you can put it this way, you can put that way. Whichever way is clear for us, we can make it like that. So now draw this one. This is minus, this is plus. This value is 3.375. This is 6.75 kilonewton meter. See, there is a one point of contraflexure here. That means wherever there is a carryover moment, even if load is not there, if there is a far end fixed, because of the carryover moment, from here to here, half moment is carried over. That's what we have explained in MDM. Because of the carryover moment, there will always exist one point of contraflexure. Okay, now this point is over. Coming to this one, due to UDL alone, first draw. UDL alone, it is like parabola, WL square by 8. We know that formula. WL square by 8 means W is 12, L is 3, square by 8. So 9 plus you will get around 13.5. Okay, this value is 13.5 kilonewton meter. Simply supported beam subjected to UDL alone. Then in addition to UDL, there are end moments. Here 0, here 6.75 hogging. See, section left side anti-clockwise, it will hog. On the same diagram, you can superimpose hogging moment also. 6.75 means like this. See here, if this is 6.75, this has to be 6.75. The area that got overlapped, you cancel. The area that didn't get overlapped is your net bending moment diagram. The area that didn't get overlapped here is negative. This is positive. Like this. See, this BC member behaves like a propped cantilever. Only difference is at B, instead of fixed end moment, you have some other moment. Because of that, it is rotating, but it behaves like a propped cantilever subjected to UDL. Strength of materials you have studied, in a propped cantilever subjected to UDL or point load, there will exist one point of contraflexure. So that point of contraflexure is here. Okay, this is your bending moment diagram. In this bending moment diagram, number of POC, points of contraflexure, are 2. This itself is a 2 marks question. They give you simply a frame like that. How many POC are there? Then we should not analyze completely and draw bending moment diagram and waste time, then calculate number of POC. Individual members you have to see. AB member, because of the carryover moment, 1 POC. BC member alone, if I see, it behaves like a propped cantilever. We know propped cantilever 1 POC. So 1 plus 1, 2. That's all. It should not take more than 10 seconds time to know how many POC are there in the structure. Such simple questions only they will give us. So we don't have to worry. So 2 points of contraflexure. Next, the deflection profile. Deflection profile. Now you see, at this point there is a point of contraflexure. Generally, the Bendman diagram deflection profiles are drawn side by side. See, from here to this up to this point, okay, up to that point, there is positive bend moment. That means this beam must sag. You stand here, it should look like a sagging. You see, in the process of sagging, if it goes inside, say, then it will hug. So you should not, beam cannot go now inside, it has to go outside only. This point cannot move left or right because see, you are fixing, any support is there. So B cannot sway. So B should be kept as it is. This should sag, this should hog. See here, plus means sagging, minus means hogging. So that hogging means from here to here when you are hogging it, see, it is a hogging, and this must sag and slope should be 0. In the process it's going up like this up to here. This is called point of inflection. This is called point of contraflexure. Point of contraflexure is shown in BM diagram. Point of inflection is shown in the deflection profile. Next, see here, if it hogs, when no load is there at the rigid joint, if one member hogs, other member has no choice. It must also hog. Okay. Because if this acts like this acts opposite side, both will hog or both will sag if there is no external load or external moment at the joint B. So from here to here it should hog for some distance, then other portion it should sag. See here, hogging means I must show it like this. It's hogging, 90-degree angle should be maintained, then it should sag this way. It must be a smooth curve. Okay, this is one point of inflection. So it's a hogging. See here, if this joint, if this rotates by theta b, let us say, if you drop here a tangent like this is also theta b. This theta b rotates, this also theta b it will rotate. This is called again point of inflection, POI. Okay, this is your deflection profile. Okay, next, axial thrust diagram. That also sometimes they will ask you. ATD. ATD means axial thrust diagram. Even in the axial thrust diagram also, two independent strength of materials, you might have drawn already axial thrust diagrams. Two independent members, what are the axial forces in that member at different locations? Those axial forces you show as a graph. Now, coming to this member AB, what is the axial force? See, AB member is subjected to axial force of 20.25 compression. BC member is subjected to axial force of 2.53. On this member 2.53 is shear force. The same shear force will act as a axial force. and here axial force is 20.25. Same axial force will act here as a shear force. Depending, same force can act as a shear force or axial force depending on which member you are considering. On that member, is it along the axis of the member? Then axial force. If it acts perpendicular to the axis, it becomes shear force. That's what we have studied in SM. Along the longitudinal axis of the member, if a force acts, it is the axial force. Perpendicular to the longitudinal axis, if any force acts, we want to call it as shear force because it acts parallel to the cross section. Okay. So now axial thrust diagram, AB member 20.25. Compression we take say negative. This is also 20.25. Next, BC member 2.53 minus. This is 4 meters. This is 3 meters. A, B, C. Like that. So now you have understood how to draw shear force diagram, Bending diagram, deflection profile, etc. In the exam, two ways of asking the questions. First one is they give you the frame. What's the moment at A? 2 minutes you have to complete. Second way is they give the moment at A 3.375, 6.750, they will give the moment. Then what is the shear force in the member AB? Shear force is 2.53. Or they will ask you what is the axial force in the member AB. Then quickly you should draw this diagram. You should get 20.25 axial force. Like that, any one particular quantity they will ask. Entire diagram they will not ask you to draw. Entire diagram is for 20 marks. One small piece is for 2 marks. We will see later on how we have to complete in 2 minutes time a specific problem. This is complete fundamentals, how it has to be solved. Now, here in this problem, I have given you POC 2. Now, we want to find number of POC without drawing the Bending diagram, etc. because that much time we will not have. By inspection, how to find the number of POC? Now you see, there is whatever moment at B you applied, half moment is carried over. Because of the COM concept, one POC will develop. That we have to remember. This is how the questions will come. Number of POC are. Assume that we have a member like this A, B, C. That's all. Lens loading, nothing will be given. That's it. Now you see, individual members you have to see. BC member is a rigid joint. That means moment will develop. Moment will develop here. That means BC behaves like a fixed beam. We have studied in the last chapter fixed beams subjected to loading, either UDL or point load. Number of POC are 2. So here 2, here whatever moment at B will develop because of COM, at A one moment will half the moment will come. So one POC for the member AB. So total number of POC are 3. So that way. So this how you see here. Number of POC in BC, or otherwise total will write. Number of points of contraflexure is equal to 3. That's all. Directly I am writing 3. Now we will write here. Why 3? BC behaves like a fixed beam. Like a fixed beam subjected to UDL. So, number of POC in BC is equal to 2. Next, due to carryover moment concept, number of POC in AB is equal to 1. So, 2 plus 1, 3, like that. Okay. Now you see, if at all, next question we will take it. Number of POC. Assume that now you have a frame like this, subjected to some point load W, A, B, C. AB member, because this B is a rigid joint, so AB member behaves like a fixed support subjected to point load. We know number of POC are 2 here. Now whatever moment B at B is there, will the half moment carried over? Since carryover moment is 0, no point of contraflexion in the member BC. So total number of POC are 2 plus 0. Number of POC is equal to 2. Reason is this one. AB behaves like a fixed beam. Fixed beam subjected to central load. So, number of POC in AB is equal to 2. Next, since C is a hinge support, no carryover moment at C. So, number of POC in BC is equal to 0. Now, you understood how to find the number of points of contraflexion in simple cases. They give you a question so that you will be able to see or easily identify member wise. Then add the individual POCs, total you will get it. Very complicated questions where sway is there. If the frames sway, then there will be sometimes POC may be there, POC may not be there depending on the span and magnitude. Such cases, they will not ask because not only you, nobody can find whether POC can develop or not. If at all frames sway, the entire moment distribution, final and moment distributions are different. So final values are different depending on those magnitudes, the deflection profiles will change. Once the deflection profile changes, whether POC develops or not, depending on the magnitude of say sway, it changes. Such questions anyhow they will not ask, but what they ask you is the bend moment diagrams. For a complicated frame, is the bend moment diagram say. If there is a fixed support, you should show some moment. Rigid joint, one member whatever negative moment you show, other member same negative moment should be there. Then if UDL is there, parabola variation. That's all. Then you can easily identify what is the correct BMD for a given frame. So now Now, having understood basic fundamentals and how we have to solve the problems, now let us try to increase the speed of solving the problems. Allotted time question is 2 marks question. You must finish off in 1.5 minute time. Now, in the process, let us see how to find them. Axial force in AB is, so they give you the frame. This is the member, let us say A, B, C. Length is L, moment of inertia I, L, I. And we have applied a moment of 2m. A clockwise moment 2m is applied. Okay. Now that first step, fixed end moments, second step, distribution factors, that story we cannot write in the exam. By seeing that itself, we can read how much they are. On the span AB, is there any applied load? If there is no applied load, no fixed end moment is required. When you apply the load, then rotation will happen. Then you have to apply some fixed end moment to make the slope 0. If no load is there, slope is already 0. Okay. So no fixed end moments will develop at A and B due to applied loads on the spans. 2m is acting at the joint. So that load is different. On the span, if any load is there, then they will bend and you have to apply some fixed end moment. So MFAB, MFBC, both of them are 0. MFBC, MFCB also 0. So all fixed end moments are 0. So first step is over. Next, second step, distribution factors. This is the footing member. Footing I told you 1, member 0. So 1, 0. At B, Li, same strengths. So when you are, if at all you apply some moment, both members will share the moment equally, 0.5, 0.5. But here, entire moment is taken by the support only. On this support, if you apply 1000 kilonewton meter, nothing goes to the column. Entire thing, support only will resist and take and keep quiet. But whereas if you apply at B, both will share because distribution factors are 0.5, 0.5. At C, this is not a footing. Footings cannot be kept horizontally, it is a wall. Wall stiffness also infinite stiffness, we take it because 3 meters by 4 meters, big walls are there. So stiffness is very large, we take it. So wall stiffness 1, beam stiffness 0. 1, 0, 1, 0, 0.5, 0.5. So we should not write as I have written in the earlier problem, distribution factor, one is footing and member. You don't have to explain to anyone whether footing is there or wall is there. Okay. So second step is over. Next, third step, end moment distribution. Most of the some problems you have to draw the table, but otherwise if movement only is there, say, the drawing the table is also not required. So now directly we will go to the third step. You don't have to write completely end moment distribution in the rough work. EMD enough. End moment distribution. This is one member, another member. Now you see A, B, C. At B, you applied a moment of 2m. Now this is what we have applied. We went and applied a moment. It is not a fixed end moment. Fixed end moment is a moment developed by the support on the member to make the slope 0. That moment, applied moment, totally different. Applied moment is what you went and applied. So at that point, when you go and apply 2m moment, how both members will share? Because 0.5, 0.5. So here it will take m. This fellow will take m. This is m, this is m. That's how they share. Further, you don't have to write a table and waste the time. When you apply m here, its share, how much is carried over here? M by 2. This is called COM. And out of this, how much is carried over? M by 2. COM. That's all. And moment distribution is over. Whatever 2m you applied, how it distributed, you have seen. Now, you have to take the fourth step, support reactions. This is our standard procedure. One member, another member, A, B, B, C. Now show the moments also. Here it is M, here it is M by 2. Here it is clockwise M, M by 2. Now see, he is asking, now we have done free body diagram. Only axial force he wanted. So entire story we don't have to write. Entire free body diagram. Whatever is required that we will show. To know the axial force in this member, take this free body diagram. M and M by 2. Total is 1.5 M clockwise. To balance it, anti-clockwise. See how your fingers are moving down, up. So here it is 1.5 m is the total moment. M plus M by 2 is 1.5 m. Both of them are clockwise. M by span is L. So 1.5 m by L down. Here 1.5 m by L up. Now you see anti-clockwise couple is 1.5 m by L into L. 1.5 m anti-clockwise, clockwise 1.5 m. Completely in equilibrium. Now who will give this 1.5 m by L to this member? This only should give like that. So in return, what this fellow will do, what here it will be done is, this is to be balanced. So 1.5 m by L. If this fellow is pulling him down, this fellow must be pulling him up. Otherwise, it will not be in equilibrium. Now these two members, if you shunt them, this and this will balance them out. Net force is 0. See, in the actual diagram, no force, no applied force. That means these two reactions must balance themselves when you join them. If 1.5 m by L upward, here downward, 1.5 m by L downward. Now this is also completely in equilibrium. He is asking now force in the member AB. So 1.5 m by L tension. Arrow mark is away. So in 2 minutes time, our task is to draw this diagram, show the EMD, draw these two free body diagrams and show what is the axial force. This is for 2 minutes time. Suppose it is not necessary that they should ask only the axial force in AB. If they ask in BC, let us say, then we could have done like this. This is another problem. Clockwise, clockwise. Total is 1.5 m by L clockwise. Balance it anti-clockwise. So this is 1.5 m by L right side. Here it should be 1.5 m by L left side. Now to keep the joint in equilibrium, here it should act 1.5 m by L right side. To balance this one here, 1.5 m by L left side. Now you see what is the axial force in the member BC? Same magnitude only, but compression. They will ask you like this: 1.5 m by L tension, 1.5 m by L compression, like that. So not only the magnitude, its nature also you have to see. Is it compressing the member or pulling the member? Okay. Next, we'll see the deflection profile. How the deflection profile goes. This is our additional problem. Slope at B we want say. This way also they can ask. This point let us say A, B, C. Here M is there. Here the moment is M. Here it is M by 2. Once its moments are known, you can assume that, as I told you, this AB member you cut it, throw it out. Not required at all. Because BC share we have already known. Now you see, this is fixed. This is like a, once its share is known to us, whether AB is a steel beam or aluminum beam or gold beam, we don't have to worry. Due to this M alone, that rigid joint rotates. So this will rotate like this. If it is a pin joint, say, what is the difference? More rotation will be there, because rigid joint, so relatively less, because share you have already taken. This profile I told you, I asked you to remember. Far end is fixed, no deflection here. Then slope is, for this type of profile, theta b is ml by 4ei. If this rotates so much, this also must rotate in the same way. 90-degree angle it should maintain. This is also theta b. Theta bc, theta ba, let us say. Theta ba or theta bc both will be same. So they till now what they didn't ask is this one, slope. This moment, what's the axial force they have asked. Once axial forces and reactions are found, draw the profile, deflection profile. That deflection profile will tell us what should be the magnitude of the slope. If this behaves now like a propped cantilever, no deflection is rotating. Like a prop, only difference is in the prop cantilever, moment is 0 at the propped end. Here some moment is there. But that profile we know. When moment is acting, it is ml by 4 ei. So we should be able to answer that as ml by 4 ei. Now I remove this one. Next point is slope at C is. All of them are 2 marks questions. Once they asked in engineering services and civil services like that. A, B, C. Length is L, I, L, I. You applied now a moment M. We want to find what is the slope at C. Time is again 1 minute time, let us say. First step, fixed end moments. Since no loads are there, no fixed end moments. Distribution factors, pin support. So for the pin support it is 0, AB1, CB1, at B, Li, far and hinge. So 3 by 4 I by L, 3 by 4 I by L. So distribution factors are 0.5, 0.5. You don't have to write that point. Then EMD. End moment distribution. First you have to distribute the moment and draw the deflection profile. When you apply M, what is the share of BC and BA? This fellow will take M by 2. This also takes M by 2. Okay. Now we want to find slope at C. Because of this M by 2, the deflection profile we know. It bends like this bends like this. For this profile, when far end is hinged, we have already learnt that at the point of application of the moment, this you worry, you cut here, throw this piece out. We are not interested in the AB member, only BC member. Individual member deflections also you can find and attach them. Frame deflection profile you will get. Because individual member moments we know, that means its profile also we can write independent of the other. So this is like a simply supported beam subjected to some moment m by 2. At the near end, theta b, if you take it, this is clock is rotating like this. What's the formula theta b? ml by 4 ei, where m means m by 2. ml by far end is hinged, so ml by 3 ei. That means this value is ml by 6 ei. But question is not theta b, theta c he is asking. Theta c. What is the standard formula? ml by 6 ei, where m is m by 2. M into L by 6 ei. M means you applied only m by 2. M you should not write because that m got distributed. Now only m by 2 is there on the member BC. So you will get ml by 12 ei. So theta c is ml by 12 ei. This is a 2 marks question. So you have to be careful. If you know the deflection profile, end condition hinge is there, here you are applying a moment. It is like now simply supported beam subjected to moment m. Rigid joint is there, m by 2 moment. Now I can read that as a simply supported one, applying some moment m. Behavior is same, like that. Okay. Now it is not necessary that I values must be same for all problems. Now let us take one more problem where I value we change it. This I think we finished. Now you see, next question is slope at C is this value we change it to 2i. This is length is same but I value is different. Now compared to this is 2 times stronger. So distribution factors we have to find. It is not 0.5, 0.5. How to find quickly? K is I by L. 2i by L, I by L. So summation is 3i by L. This is K by sigma K. So 2 by 3. This is 1 by 3. Supposing that this much fast you could not make it. First I show you how we are calculating, then by inspection you will know how to manage in the exam. See, distribution factors. How it changes? Joint, member, K, sigma K. Distribution factors are K by sigma K. So joint B. So member BA, its K is I by L we have to write. BC member 2I by L. See I 2I. What is the sum? I can write 3I by L. This is 1 by 3. This is 2 by 3. So BC is 2 by 3. BA is 1 by 3. With this what to understand? Sum is 3. Individual is 2. So 2 by sum. This is sum individual 1. Sum is 3. So 1 by 3, 2 by 3. Now you understand how that 1 by 3, 2 by 3 came. When I read it, supposing that for those who didn't get clarity, I have drawn this diagram, how we are getting. Now observe. 1, 2, total is 3. Then 1 by 3, 2 by 3. Like that. This is 2, 1. Total is 3. So, this is 2 by 3, 1 by 3. Next, EMD, end moment distribution. Now see the frame here. This is a hinge support. This is also hinge. This point is A, B, C. Now out of M, this fellow will take 2 by 3 distribution factor. So 2/3 of M. This is 2M by 3. This will take M by 3. So end moment distribution is over. But he is not asking EMD. Slope at C. Now draw the deflection profile like this. This is theta B. ML by 3A formula, where M means 2M by 3, ML by 3E, I means 2I. Then theta C, ML by 6EI is the standard formula, where ML by 6EI, where M is only 2M by 3. ml by 6 ei means 2i. So you will get ml by 18 ei. And theta b will get 2 cancels out, ml by 9 ei. This is ml by 18 ei. Here also same thing. It will also deflect in the same way. The moment is so adjusted that this theta b is also same. ml by 9 ei. Then half of that. Theta a again you will get ml by, out of this half will be carried over here. ml by 9 means ml by 18 ei, like that. So you see here theta a if you want, m means m by 3, l by far end is 6 ei. So ml by 18 ei. So they can ask you theta c or theta a or theta b, anything. But once you draw the profile, formulas, this I told you to remember for a simply supported beam subjected to moment m. At the application of moment m, ml by 3 ei. Far end, half of that, ml by 6 ei. Then what is the m? Individual values you substitute, you will get the result. Next. Next one is this one. Axial force in BC is, assume that this is a floating hinge. Internal hinge we can write, because not floating, simply internal hinge. A, B, C. This load, let us say 10, 2 meters, total is 4 meters, I, 4 meters, I. We have a frame now, but at B there is one internal hinge. Now you see, two ways we will solve, depending on which idea you get in the exam. For this, understanding points are like this. This what you have studied in strength of materials. Assume that in a propped cantilever beam, if you have a hinge support subjected to some central point load W, L by 2, L by 2. Same thing we get in the plastic analysis also. This is the deflection profile. For this profile, you have studied this point B, say this is say A. What is VB? 5W by 16. This one, MA, 3WL by 16. Assume that you have remembered these values. This is the for this profile subjected to central load, these are the values. Wherever you see this type of profile, moment should be 0, deflection here the deflection is 0, free to rotate, moment is 0, fixed support, this is the profile, central point load, this is the fixed quantity. Now this problem and this problem, only difference is there is a hinge support here. Here what happened, instead of that support, what it is we have shown. Here it is resting on a column. This is a column generally. Instead of showing entire column and wasting the time, simply hinge support you will take it. Support means it should rest on something. That resting place is the column. We have we can take it that way. Now you see, if I draw the deflection profile, A, B, C. This load is 10 kilonewton, 2 meters, 4 meters. Now you see, only AB profile if I draw, it will go like this. See, this profile match. If deflection profiles match, forces also you can match. Okay. Now, if you draw the free body diagram of each member, I'll show here. First member, this is the load here, 10 kilonewton, 2 meters, 4 meters, this point A, B. Now we know how much reaction should be there here. VB is equal to 5 W by 16, 5 into 10 by 16. So 50 by 16 means 3.12. Now VB is the force exerted by the column on the member AB. Now if I draw free body diagram of AB, this is how it looks. Free body diagram of BC. So if VB is acting upward here, it should act downward here. 3.12 down. To balance it, 3.12 up. No movement here. Here no movement. No movement. So BC member behaves like an axially loaded member. So force in the member BC is 3.12 kilonewton compression. Like this. Supposing that this idea we didn't get, strength of materials idea we didn't get. Okay. Then we can use the MDM also. That let us see now. Second method, end moment distribution. Joint, see A, B and C. Distribution factors. At A it is 0. B and BC, what we have to do? BA 0, not even 0, nothing we have to show. Why? I told you in the class that the distribution factors are defined for members meeting at a rigid joint. At B there is a pin joint. If at all you apply movement, the pin will rotate, nothing will be distributed. So no distribution factors. Distribution factors are defined for members meeting at rigid joint only. So no distribution factors. C we can take say 0. Now fixed end moments. MFAB WL by 8. So you will get minus 5 plus 5. WL by 8 means that 0, 0. Now you see, individually you have to release. At B, to fix it, plus 5 is required, minus 5 to fix it. But B is not a fixed support, you see, is a hinge, so release. Don't sum them, even if load moment is there also, we should not worry. Whether there or not, individually you have to release. So release B. So release B means to fix it plus 5, to release minus 5. Minus 5. Here nothing, no release at all, nothing. So when you apply minus 5, how much is carried over to the far end? Carry over moment. Minus 2.5. That's all. After that, work is also over. Now final end moments. Minus 7.5. 0, 0, 0. This is the final end moments. Next, after finding final end moments, to find the reaction at B means you have to draw the free body diagram. So free body diagram of AB. AB alone is sufficient. AB if you show, then BC also if you want you can show like this. A, B, B, C. There is a downward load of 10 kilonewton. 2 meters, 2 meters. Now you see, due to 10 here reaction is 5. Here also reaction is 5. There is a moment of minus 7.5 here. Okay. Now due to moment anti-clockwise, so clockwise reactions will develop. This is upward, here downward. How much? 7.5 by 4. 1.875 like this. This also 1.875. Okay. So now net force we can find here. Net upward force is approximately around 3.125. Okay, 3.125 up, and this is the resultant force. If this is 3.125 upward, here it should be downward, here it should be upward, 3.125. So force in member BC. Compression. Such cases where internal hinge is there, say, then you have two options. If you know the deflection profile, if you know that 5W by 16 formula, you manage it. If that idea doesn't come, then use MDM. Release the moments individually. Here you have to release fixed end moments individually. For fixed release, this has, if at all moment is there, fixed release. First fix, then release. Individually you have to release. Individually release means, let us see one more problem where load is also on this span. Then more clarity you will get. So after finding this one, then this free body diagrams you have to draw to find the force how much. First you will get this force 3.125, reverse it on the member BC. So it's an axially loaded member. Because moment is not transferring, then axially loaded member it behaves. Okay. Now let us see. We will apply one more load here and find moment at A. This 3WL by 16 we will try to make use. That 3WL by 6 in the plastic analysis also will explain 3WL by 16, and here you will get center point 9WL by 128. For all positions of the loads, the fixed end moment is always more than the positive bending moment. When if you imagine that the point load is moving from one end to the other end, under the point load positive bending moment, here negative bending moment. Wherever load is there, negative bending moment is always more than the positive bending moment which occurs under the point load. Now let us see one more question. Moment at A is again floating hinge, will keep it. Same load 10 kilonewton. This point let us say A, B, C. We'll keep one more load here, say 20 kilonewton. 2 meters, 4 meters I, 2 meters. This is total 4 meters I. Now, as I told you, if you know the deflection profile, first method, 10 kilonewton, 2 meters, 2 meters. This point say A, B, C. Now, whether 20 is there or not, axial forces, because of 20, there will develop axial force only, no moment. But axial deformations we will neglect. So, the deflection profile is something like this. Whether this load is there or not, this profile will not be influenced, will not be affected. So, for this profile, we know the reaction is 5W by 16. Moment at A is 3WL by 16. So, directly we can write moment at A is equal to 3WL by 16. 3W is 10, length is 4 by 16. So, 30 by 4 means 7.5 kilonewton meter. 2 minutes time we can easily manage. If you show this profile also, similar to this, you will get this one. It will go inside because the individual free body diagrams, individual deflected shapes will not be influenced. Because load is there, it will bend like this. If load is not there, it will bend like this only. This is straight line. That's all. See, a slope 90 degrees we need not maintain because it's a pin joint. And distribution factors, MDM distribution factors we cannot find because it's a pin joint. As I told you earlier, if there is a pin joint, on the pin you apply moment say 100 kilonewton meter, then that pin will rotate like a shaft. Half the movement will not be carried over. Nothing will be carried over. All the members simply keep quiet. The pin will rotate like a shaft. So, if you have a rigid joint, then on the rigid joint you apply moment, then the question of sharing will come. Otherwise, nobody will share anything. Okay. Now, this is the first method. Now, let us see the second method. Assume that this 3WL by 16 you have forgotten. Now, we will go for MDM, end moment distribution. Joint, member, directly we will write this one. This is A, B and C. Distribution factors are, here it is 0, here no distribution factors. Reason is same, here it is 0. Next, fixed end moments. Here WL by 8 means minus 5 plus 5. Now stand here, when you apply, for this profile if you apply moment, fixed end moment, it is anti-clockwise. WL by 8. So 20 into 4 by 8 means what? 10. So minus 10 plus 10. This minus 5 plus 10, they cannot be released because they are fixed support only. But at B, pin joint, both members we know that moment should be 0. BA, MBA, MBC, they have to be 0 because it's a pin. But unnecessarily you fixed it. To fix joint B for the member BA alone, plus 5 is required. To fix BC member at B alone, you require minus 10. Now release the moments independently. That is called release. Release B. When you are releasing it, you should not sum it. Minus 5, sum is minus 5. So minus 5 into how much you will do? No distribution factors. So don't sum them. Individually you release. Plus 5 to fix it, minus 5 to release it. Minus 10 to fix it, plus 10 to release it. Like this. That's what I meant. Release independently. Release fixed end moments independently. Okay. Now, once you release it, release means who will release? We only have to release. You went and applied minus 5. Then how much is carryover moment? Because this is a free fixed support. Minus 2.5 plus 5. That's all. After that, nothing is there for us to manage. So now you will get final end moments minus 7.5, 0, 0, plus 15. See what's the moment at A? Simply, they don't ask you plus or minus. Simply 7.5 kilonewton meter. This way is one thing. This way 3WL by 16 you remember the same result you will get. Because this profile we know. So we could have written. We have written that way. If this idea you don't get it, this we can make it. Just fix all of them, then release at B independently. Then half moment is carried over, issue closes. Okay. Now let us see. Now let us see one more question. Moment at A is you applied A. This point let us say AB, center point is a C. L by 2, L by 2. Okay. Now, how to finish off this problem? Same thing. This point say A, B, C. We solved earlier one problem. AC horizontal, BC vertical. Then when you apply momentum, both shared equally. m by 2, m by 2. Then for carryover moment is half of that. Okay. Now instead of 90-degree bend, you have 180-degree bend, you assume. CA is one member, CB is another member. Instead of connecting like this, they are connected like that. Still, your moment will be shared by the two members equally, because L by 2, L by 2, I. That means whatever moment you apply M, both will share equally. So now, first step is fixed end moments. This 0, 0. Then distribution factors 0 0.5, 0 0.5. End moment distribution, M here it will come to M by 2 clockwise, M by 2 clockwise. How much is carried over? Half of that. M by 4 here. How much is carried over here? M by 4. So moment at A is M by 4. 2 minutes time. Okay, just distribute carry moment. Then supposing that if they ask you slightly difficult question, what is the slope at C? Slope at C is. Now you see, for that, only for this problem it is valid because of this reason. When you apply a moment M, see how my fingers are moving like this. This go down, this will go up. Because of the lengths being same, I value same, at center slope will be 0 like this. This is the deflection profile. Out of this fellow will take M by 2. This will take M by 2. This point A, C, B. At C point, deflection is 0. For such cases, you can stop the work like this. If it deflects, that means instead of center some other location if you want, then it deflects, then it becomes a 20 marks question. Only at center, we can simplify, complete in 10 seconds time. So now slope at C. This is the deflection profile. At C, deflection is 0. Now cut here, throw this piece out. This piece alone is looking like a propped cantilever whose length is L by 2, subjected to a moment M by 2. For this profile, we know how to manage ML by 4EI. This is theta C he is asking. Since both of them are same, cut, throw it out, take only this portion. It is now like a propped cantilever subjected to a moment M by 2 whose length is L by 2. So now theta C is equal to ML by 4EI, where M is M by 2, length is L by 2, ML by 4EI. So you will get ML by 16EI. Sir might have told you that formulas on list they might have given, but to remember them easily, this is how you should manage. Deflection at C is 0. Okay, like that. Now, similarly, one more problem. Let us see. A simply supported beam, we will take it. Slope at B is. You apply a moment M. This is say A, B, C. If you want to find slope at B, the deflection profile is a 2 marks question. Say deflection profile is like this. Okay, here deflection will be 0. Now, out of M, this length is L by 2, this length is L by 2. how much moment it will take out of m? This member will take m by 2. This will also take m by 2. So your m gets distributed m by 2, m by 2. Here deflection is 0. Cut, throw this piece out. Now you have a small beam CB whose length is L by 2, subjected at one end a moment of m by 2. When far end is hinged, what is the formula? ml by 6ei. Theta b, your standard formula is ml by 6ei. This is your standard formula. Now you see what is m here? M by 2. M means this is when m is applying, but you have applied m by 2. Length is L by 2. ml by 6ei. So theta b will get ml by 24ei. If you want to find theta c, formula is ml by 3ei. So you will get ml by 12ei. How we could write this? Deflection profiles will tell us what should be those values. These formulas ml by 3i, ml by 6i, if you remember, wherever you see that type of deflection profile, those values simply attach them. Okay, like this. Now we'll see one more problem. Moment at A is this point, let us say A, B, C. Let us say this force 4 kilonewton. This is 2 meters, 3 meters, 4 meters. I. In one of the civil services, it was a 20 marks question. That means you have around 5 minutes time to draw. That means there 5 minutes time is given, means you must draw SFD, BMD, complete analysis we have to make it. Now we wanted only moment at A. Can be finished in 20 or 30 seconds time. Let us see how to find that, how to finish off quickly. If not understood, again we will draw completely. Then I will explain how we have to read it. In any beam, overhangs are there, we neglect them. So we will cut here, remove the overhang, replace it by its effect on the beam. So this is equivalent to this one. So 4 kilonewton down, and moment is 8 kilonewton meter. This point A, B, C. This is 4 meters I, 3 meters I. Right? This is what we get it. I told you in the earlier problem, wherever you set a rigid joint, this is like a rigid joint. ABC is at ABC is a single member. At B simply there is a support was there in the form of a roller support, but ABC is a single member, no two separate members are added. Okay. Now, if you stand at B, look at A, far end is fixed 4 meters, I. Stand at B, look at C, far end is hinge 3 meters. So, 4I, 3I means 0.5, because it's a hinge support. Okay. So, that's I told you, explained this is 3 by 4, I by 3. 3 by 4, I by 3 means what? I by 4. I by 4. So, 0.5. Okay. So, that we at least one problem we are expecting that you have done it. That means that much working experience must be there. Okay. Now, at this C, what is the process moment distribution? We lock all the joints, no applied loads. We lock all the joints, only at one end applied moment 8. Thinking that it is a locked one, when you apply 8, this is applied. How much of that is carried over here? Half. 4 is carried over. So, it's thinking that is fixed, 4 will come. But B is not fixed, release. Once you release, how that 4 gets distributed? 0.5 means 2. So, at B for the member BA, you will get only 2. How much is carried over here? 1. 2 will be carried over, half will be carried over. So, moment at A is simply 1 kilonewton meter. That's all. By inspection, we can get it. Cut, throw it out, 8, half will be carried over, 4 gets distributed, 2, carry over 1. Assume that you didn't understand what we talked. Then we have to do it like this. Complete solution I am taking. Your first step is fixed end moments. MFAB, BA, BC, CB 0. MFCD span, this is like this. This is 4 kilonewton, 2 meters. This is CD. Clockwise, so it is anti-clockwise. MFCD, anti-clockwise, so minus 8 kilonewton meter. All other values are 0. Then second step, distribution factors, joint, member, K, sigma K. Distribution factors are K by sigma K. This is what I told you, why 0.5. So, only one member, one joint you have to take. BA, stand at B, look at A. Far end is fixed, I by 4. B, C, stand at B, look at C. Far end is hinge, 3 by 4, I by 3. So, you will get I by 4, then 2I by 4. So, 1 by 2 is 0.5, 0.5. So, this much we should not do and tell that it is 0.5, 0.5. Then third step, end moment distribution, joint, this point let us say A, B, C, D. Distribution factors. It is 0, BA 0.5, BC 0.5. CB, it is 1 because only one member. This is free end. If far end is free, distribution factor is 0. Nothing here because no support. Why 0? I told you earlier, if far end is free, its distribution factor is 0. So, that is why it is 0. Now, we will write all the fixed end moments. There are no loads on the span AB. So, 0, 0, 0, 0. MFCD minus 8, nothing. So, to fix AB span and BC span, you require 0 moments. To fix CD span, only at C, not at D, because when far end is free, that free end we should not fix it. Except free end, all joints will fix them. That's what I have given you in MDM procedure. So only C when I fix it, I have to apply minus 8. Then at C for the member CD, slope becomes 0, 8 kilonewton meter. Now when you see this problem, C is not fixed one, but minus 8 is to fix it. So release C. So release C. Minus 8 is to fix it, plus 8 to release. When you apply plus 8, how it will be released? How it will be distributed? You apply plus 8. Plus 8 means clockwise. Plus 8 into 1 is 8. So plus 8. Plus 8 into 0 is 0. So this is 0. So this is how it gets distributed. So release C. Then how much is carried over? So this release plus 8 means we apply now plus 8. That plus 8 is similar to this plus 8. Okay. Here problem directly we started from here. There we wanted to start from the beginning without cutting the cantilever, plus 8. How much is carryover moment? When you apply 8, how much is carried over? Half of that, plus 4. Now thinking that B is a fixed one, out of it 4 came in the form of a fixed end moment. But B is not fixed, so release. That is called release. Release B or balance, whatever way you want to use that balance. Plus 4 is to fix it, assuming that the joint B is locked, plus 4 is required, so unlock it. So minus 4 when you apply, you will get minus 2, minus 2, minus 2. Now when you apply this minus 2, you have applied. When you apply minus 4, this took minus 2, this took minus 2. So at B for the member BA is minus 2. When you apply minus 2, how much is carried over? Half of that, minus 1 here. Because see, you are treating it as hinge support, then it is 0. So COM is minus 1. So that is the work. Next, final end moments. Final end moments. What are the final end moments? Minus 1, minus 2, plus 2, plus 8, minus 8, nothing. So moment at A, they will ask you whether plus or minus, they will not ask you, simply 1. Moment at A is 1 kilonewton meter. So this is what I told. This much we can read in 10-15 seconds time itself. This is actual textbook procedures, means like this we have to do it. But you will be pressed for time, only 1 minute time is there. This is the process. Cut, throw it out. You get 8. So out of 8, you fix this one. 4 will come. 4 gets distributed. 2, 2. See, 2, 2 it became. Out of 2, carryover moment is 1. So directly you can write 1. But that if you want to write it like this, you have to write like that if it is a 20 marks question. If it is a 2 marks question, you don't have to explain to anyone that process. Simply one you answer. Like that.